This is our first lecture this week. We have completed the parts on raw materials and manufacturing of composite structures. We have introduced certain raw materials for composites manufacturing, including fiber and matrix materials. And we have also talked about various manufacturing methods, and ready-to-mold sheets are also considered because ready-to-mold sheets are used in wet layup methods or compression molding procedures. In the second part of the course, we will consider analysis and design of composite structures. We will start with a single lamina, examine the properties of a lamina, and then we will see how constitutive relations, stress-strain relations can be written for a lamina using anisotropic material properties, and you will be able to evaluate strains and stresses in a lamina. That's called macromechanics. And then we will see how material properties of a lamina can be calculated. What are the models for the computation of material properties? And it is referred to as micromechanics because micromechanics deals with fibers and matrices. And then we will extend these methods to carry out analysis for laminates. A laminate consists of a number of lamina or a number of plies, and you can extend the main formulation or procedure developed for plies to compute stresses and strains for laminates. And this will allow you to do design work on laminates, or optimization type of computations can also be carried out. And, but the first part of such analysis procedures is related to macromechanical or macromechanics of a single lamina or a ply, and this is chapter 4. What is a lamina? You know what a lamina is. This is a laminate manufactured by a certain processing technology. It could be a simple hand layer or pre-preg layer or any other suitable composites processing technique. In pre-preg layup, each lamina is actually a pre-preg. And you can stack these in different directions. For example, in the mid lamina, fibers are oriented in the longitudinal direction. In the first ply, the fibers are orthogonal. This is a cross-ply laminates because fiber angles are either 0 or 90 degrees. We have a number of plies, and thickness of each ply could be at the order of 0.1 millimeters, 0.125 millimeters. Now, in this chapter, we will be dealing with mechanics of a single ply. What are the equations for a single ply? But single ply, as shown here, is not homogeneous. You can say that this ply, the first ply, or the second ply, or any of the plies here is not homogeneous. Because in a ply, you have fibers as well as the matrix material. Material properties are not the same. For fiber, you have larger elastic modulus values. For matrices, different elastic modulus values. For this reason, a single lamina is not homogeneous, but in order to simplify the computation procedures, the lamina is assumed to be acting as a single homogeneous layer. And that is referred to as homogenization of a ply or a lamina. We will assume that material properties are homogeneous and average material properties are going to be considered. I'm going to assume that this lamina has an average modulus of elasticity in this direction. This average elasticity value depends on the moduli of the fiber and the matrix. But I'm going to assume that it has average properties in all directions. Average modulus of elasticity, average Poisson's ratios, average shear moduli. It is going to be modeled as a homogeneous unit. And then we'll be able to apply Hooke's law for anisotropic materials to model the single piece of lamina. But homogenization is an important concept. How can we find this average properties then? I assume that there are average properties in x1 direction and in x2 direction. But what are these average properties? Given the fiber properties and the matrix properties, how can I find these average properties? We will consider this problem in the next chapter, in chapter 5. That's a separate problem, and it's referred to as micromechanics. Calculation of average properties of a ply or a composite body is referred to as micromechanics. The material body is not isotropic. There are different properties in different directions, but these properties are assumed to be homogeneous. And macromechanics deals with calculation of displacement, stresses, and strains in a lamina or a laminate. But we have to make a distinction between isotropy and homogeneity. Any of these plies is going to be modeled as a homogeneous body, but you cannot model it as an isotropic piece of material. And what is the reason of anisotropy in a ply? This could be a question for you. Why is a ply an isotropic material? Any answers on this? Why is a ply or a composite structure anisotropic? Why is it not an isotropic body? It is because of the fibers, of course, fiber orientations in the prepregs, or the layers. This fiber reinforced lamina is strengthened in this direction, but strength is expected to be lower in the orthogonal direction. There is a dependence on direction, and we can illustrate this by considering a single lamina like this, or a single layer as shown here. This is a single layer. Now I assume that this is an isotropic material, an isotropic homogeneous material, plate. It could be steel, aluminum, the metallic material. And I cut out a small piece of specimen out of this large body of material. This small piece of material has width W and height, or this length W and width W, same in plane dimensions, and thickness is T. There's a small thickness T. I have cut this out of the specimen, and now I apply a force P on this specimen, isotropic homogeneous specimen. Its original dimensions were W. Then you apply this force, it's going to extend in the longitudinal direction. And I'm going to show the new length as W plus delta 2A. Delta 2A is deformation. Total displacement on the specimen is delta 2A, which is a positive quantity. But because of the Poisson effects in the transverse direction, there is going to be a contraction. And the new dimension, the new length here, is shown as W plus delta 1A. Is delta 1A positive or negative? Any answers on this? Is delta 1A positive or negative? Yes, Hussein gave the correct answer. That's because of fiber's direction. Is delta 1A positive or negative? That's, of course, negative because of the contraction. As specimen. These are elastic formations, and now I'm loading the same specimen in a different direction. In one direction. Now, the vertical direction is shown as 1, horizontal direction is shown as direction 2. Load it in one direction, sorry. Apply the same force, and the specimen will undergo new deformation, and length on this side is going to be W plus delta 1B, and length of this side is W plus delta 2B, as shown here. This specimen is metallic, it's homogeneous, and at the same time isotropic. And then what can you say about delta 2A and delta 1B if it is isotropic specimen? This is an extension in force direction. This is delta 1B is also extension in force direction. What can you say about delta 2A and delta 1B?
They are equal.
Yes, Serkan gave the correct answer. They are equal for an isotropic conventional material. And that's also the case for the Poisson deformation. Delta 1A here, this negative quantity, should be equivalent to delta 2B, the other negative quantity. There are no problems here. For isotropic standard materials, these total deformations are equal to each other. But the problem or situation is different when you consider a lamina here. A composite body or a prepreg is shown here. So this is a prepreg, and fibers are oriented along longitudinal direction. And I prepare a specimen out of this composite body now. Apply loading in longitudinal direction. Force is P. It's applied in axial direction. You can see the fibers here, and the force is applied in the direction of the fibers. And total deformation is again delta 2A, and total deformation in the other direction is delta 1A. This one, delta 1A. Now I can remove the force and apply it in a different direction, as you see here. I'm applying the force in one direction or vertical direction here. But the situation is not the same because this one direction is perpendicular to the fibers. The specimen is going to elongate. Total displacement is delta 1B. Now, what can you say about delta 2A and delta 1B? Are they equal to each other? They are not equal because in this direction, in one direction, the specimen is weaker. As Ali gave the correct answer, delta 1B should be significantly larger than delta 2A because we are loading it along the weaker direction. It's weak. And this is also the case for the Poisson deformation. It's delta 1B, delta 1A here. And another contraction here, delta 2B. You see delta 2B and delta 1B. If you consider the absolute values, these are negative, but if you consider the absolute values, which is larger, delta 1A or delta 1B, which is larger, A or B?
A is larger hocam.
A is larger, that's right. If you think about the absolute values, A is larger because in this direction, the specimen is weaker and Poisson effect is more pronounced for case A. This is an illustration of anisotropy of the material. It's not same as conventional isotropic metallic materials. There's another observation here, there's another phenomenon. I'm going to cut out another specimen here, but at an angle. This will be cut at an angle, ABCD. Fibers are again in longitudinal direction as shown here. The edge is at an angle to the fibers. Now, if you consider this specimen, so ABCD, therefore the fibers are not in the longitudinal direction. Now, we have even a higher degree of anisotropy here because fiber direction does not coincide with the global coordinate axis for the specimen. In this case, we have another observation. You can pull it. You can apply a force, but it will not only elongate, but it will also undergo shear type of deformation. Although the loading is pure normal stress, you will observe shear strain in this specimen. The original angle here is 90 degrees. Because of the fibers, however, this will undergo shear type deformation, and the final angle will not be exactly 90 degrees. It's referred to as shear normal stress coupling. And this is another observation for anisotropic materials. And you will see how these are accounted for in modeling. And constitutive relations have to be changed. We cannot use simple Hooke's law applicable for anisotropic elastic materials. We need to have additional constants in Hooke's law that account for the level of anisotropy in the material system. I need to talk about this. Any questions or comments on this? I'm going to review certain variables related to analysis of deformable bodies, because we are going to use these definitions throughout the semester. The most important mathematical concept here is stress in a deformable body, a state of stress. And a deformable body can be loaded by applying external forces on it. These forces can be applied to the surface of the body. They result from direct contacts with another object. For this reason, these forces are referred to as surface forces. And the second type of effect is due to a distribution of forces over the volume. These are called body forces. Can you give an example for body force?
Gravitation.
Sorry?
Gravitation body force.
That's right. That's the most commonly encountered body force. Gravitational effect. Gravity is acting on all particles of a material. It's therefore considered as a body force acting over the volume of the material. It's acting over the volume. And inertial forces, that's right, saying here inertial forces as another example. It is acceleration and resultant forces due to acceleration can be included as inertial forces in the analysis, and that's going to be another body force, because a solid body, if it's undergoing motion, each point on the body will have a certain acceleration, and you can include it, the effect due to acceleration, as a body force. And internally, you can make a distinction between surface forces and the body forces, as well. Then you cut the body over a certain cross-section, an internal distribution over the area is needed to keep that body in equilibrium. That is a distribution over the surface. Those forces are surface forces. These are also named as tractions or stress vectors, and stress gives the intensity of this internal force distribution. You have an internal force distribution, surface force distribution in the body, and stress is the intensity of this internal force distribution. You can evaluate compute stress on a surface and different components of stress can be defined on a surface. And how can we do this? We start with a loaded deformable body like this, shown in the figure. This is a deformable body. A coordinate system is attached here, X, Y, Z. There could be external forces or resultant moments. Now, I pass a section through the body. Let's say that is an arbitrary section. And I can define stresses over the area exposed here. I cut this into two. There's a free body diagram, and I consider the portion of the body lying to the left of the cut. And stress can be computed, stress components can be computed at any point on this area. And a particular point is shown here. Now, to define stress, you need, let me clear this, you need an area surrounding this point, that's delta A, as well as resultant force acting on this area, and that's delta P. There is an internal force distribution. And if I consider an area, I'll be able to compute a resultant force acting over this area. And then suppose that this is delta P. Now, this area has a normal. There's a normal direction and an in-plane tangential direction S. Any vector can be resolved into two components. One of them is perpendicular to this area, and the other is in the plane, the area in S direction. These components are shown as delta Pn with perpendicular and delta Ps. And this is the shear. Delta Pn is called normal force, delta Ps is called shear force, which means that I can evaluate a normal stress and the shear stress at this point by introducing limits. You can define normal stress at this particular point. Normal stress sigma n is limit delta A goes to 0, delta Pn over delta A. This is called normal stress at this point. And shear stress is denoted by tau S. As limit as delta A goes to 0, delta Ps over delta A. At any point, you can calculate a normal stress and shear components. These depend on the components of the force in normal direction and the tangential direction. And any vector can be resolved into two such components, a normal component and tangential component, and normal component and in-plane component of a vector can always be found. And then it's going to be possible to find or define normal and shear stress. We can resolve shear into components as well. And if a coordinate system is defined as shown here, most of the time we evaluate stress components pertaining to such a coordinate system definition. So what are the stresses defined in accordance with a coordinate system? How can I define or calculate stresses in accordance with a given coordinate system? In this case, you have to pass a section through the solid body, but the section has to be parallel to one of the coordinate planes shown here. In this particular case, the area is parallel to YZ coordinate plane. Different stress components can be calculated at the same points by passing such different planes. Stress depends on, therefore, the plane passed over that particular point. And if you consider this coordinate system, there are a finite number of stress components we can define by passing planes through that particular point. For this particular plane, at a specific point, generic point, we have a resultant force needed for equilibrium. You have resultant forces at all points. And then resolve this force into components acting along x, y, z directions. In x direction, delta px is defined. In y direction, you have the force component, delta py. In z direction, delta pz. So obviously, we can define now three stress components. One of them is normal stress, and it is going to be shown as sigma x. Remaining two are shear stresses, and they are going to be shown as sigma xy and sigma xc. Probably you know these definitions from other courses from strength of materials. These concepts are actually described in strength of materials or machine elements. And sigma x, on which force components does sigma x depend? Which of these components is related to sigma x? Delta px, delta py, delta pz. Obviously, it's delta px, right? And sigma xy is defined in terms of delta py. Sigma xz shear is defined in terms of delta pz. Limit definitions are shown here, and for shear in this notation we use tau, not sigma. Sigma x is limit delta A goes to 0, delta px over delta A. Tau xy is limit delta A goes to 0, delta py over delta A is one of the shear. Delta xc, tau xc is limit delta A goes to 0, delta pz over delta A. Vector sum of this is going to give you the net shear. But we have a convention or standardized notation for shear stresses defined at a point. It is sufficient to use a single subscript for normal stress. For shear, you have two subscripts. First one shows the direction of the normal of this plane, which means stress depends on the plane. And the second one, second index, shows direction of the shear stress. Thus, on a given plane, these internal forces, intensity of these internal force distribution is shown by sigma x tau rj. These are functions of x, y, z themselves. Now, I have passed a certain coordinate plane here, and this was parallel to YZ plane as shown. But I could have passed planes parallel to other coordinate planes. You could have passed a plane parallel to XZ, this one, and this will add 3 stress components for this point, and you could have passed another plane which is parallel to XY, and this will add 3 stress components for the same point. And it seems we have a total of 9 stress components that can be defined at this point. And in engineering notation, we show all these planes on a stress element as depicted in this picture. This is general stress states for this point. Each face of this cube corresponds to a particular plane passed through this point. We have started with this plane, and we can show stresses sigma x, tau xy, and tau xc. Well, this is the second plane, and now this contains the stresses sigma y, tau yz, normal direction notation, tau yx, normal direction notation. And these are the stresses on this phase, tau zy, tau zx, sigma z. All these are needed in a general 3D problem to define stress. In the 3D case, you could end up with these stresses, but if you consider equilibrium of the body, for example, you can show that, you can mathematically show that shear stresses on planes that are perpendicular to each other, as shown here, should be equal to each other. Equilibrium of the body dictates this condition, which means that tau yx should be equal to tau xy, and tau xz should be equal to tau x, tau zx. In a similar way, tau yz should be equal to tau zy, which means that we have how many stresses? How many stresses are needed to define stress state at a point?
6.
Sorry?
6 hocam.
Yes, that's right. Okan gave the correct answer. That's an important result. Most general case for a 3-dimensional problem, you need 6 stress components, also as Hussein written here, 3 shear stresses and 3 normal stresses, that is right. Sigma x, y, z, shear x, y, x, z, and y, z, normal and shear stresses are defined, and they are shown in a matrix in elasticity notation or in solution of problems. There's the stress state at a point. They are defined on different planes. However, stress state for a single point is completed or completely defined by this matrix. The terms on the diagonal are the normal stresses, And the off-diagonal terms shown here, there should be tau notation, tau xy, tau xc, tau yz. These are shear stresses. And this could be functions of all coordinates x, y, z, as well as time or other variables depending on the problem being examined. Now, this is the general description of stress states, and we will follow this notation, general, well-established notation for deformable bodies. And shear stresses has a certain way of representation, and the normal stresses are defined by the Greek letter sigma. So stress is the first mathematical variable needed to describe the behavior of a deformable body. And the second mathematical variable needed is strain. It is related to the deformations of the body. And for small deformations, you can start with infinitesimal vectors. You can examine behavior of infinitesimal vectors, stretch and rotation of infinitesimal vectors on a deformable body can be examined to define all strain components, but we will talk about this in the next lecture on Wednesday. So if you don't have any questions, this is the end of the lecture for today, and we will continue on Wednesday.